anything. Hopefully you don't know too much about waves. So this is the IGCSE lesson. We've done forces, we've done electricity, and yeah, we've got 12 wave lessons stretching ahead of us. I'm just going to tell you a story straight away. So the Theatre of Science mascot is Wormy, right? So I've done a little story about Wormy, and I've crammed in as many different waves as I can. And I want you to ideally write down, like, maybe just note it in your head if you really don't like writing, but ideally write down quickly as many different waves as you see or hear mentioned in the story, okay? So even if you just like hear a reference to a wave, write it down. If you see one, write it down. And then at the end of the lesson, hopefully you'll be able to like correct and spot a few more. And at the end of the module, hopefully you should have you should be like, oh yeah, I see what she was doing there, and be naming even new ones that aren't on the picture. Okay, be kind. It took me ages. Off we go. Theatre of Science presents Wormy in Trouble at Sea. Illustrations by vectc.com. Sorry, you're in a Lego phone holder, which is piled up on top of some of my business cards that have the wrong email address on. Just need to add more business cards. There we go. Right. So lots of different waves appear in the story. Please make a note of those that you see or hear mentioned. And at the end of the module, like in 12 weeks' time, hopefully you'll get them all and you will be able to spot fake waves as well. Here's Wormy. I love living on a boat. Nice calm sea today. Just ripples. I'll just microwave some soup. The radio comes on. That's what radios do, apparently, in emergency situations. Fizz! Breaking news! An earthquake has just happened. Oh no, says Wormy. So she runs to her TV remote control. Better turn on the TV. Douche. TV remote control turns on TV. Here's a newsreader on TV. Luckily, only one person was injured. They are in hospital having x-rays. Pictures of x-rays. Unfortunately, the earthquake triggered an enormous ocean wave. This is just a side note, not really to do with waves. Could only find pictures where the newsreader was smiling. So like subplot, newsreader is evil. I must get to the steering wheel of the boat. Straight away, says Wormy. I don't know the proper name for the steering wheel of a boat. I didn't when I wrote this, and I don't now. If you Googled everything, you would literally never get anything done. So she runs towards the steering wheel, but oh no, she's forgotten. She owns a massive treadmill. She gets stuck on the treadmill, making a wave-like shape with her very long now wormy body. Eventually she gets off the treadmill. She goes to the window. Oh, hooray, the lifeboat is here. Better wave and let them know I need help. You ready to watch a worm waving? Here we go. Yes, nice one, Wormy. So she just waves. And that is the end, apart from this awesome pun. Help is on the way. Yeah. So the end. Thank you very much to Olivia P for sending me that little Fimo version of Wormy. All right, so hopefully, like it would be very bad for me if you already knew all the waves in the story, because I wouldn't be able to teach you anything. But hopefully you've got a few waves. So I thought we'll start by talking about sound, because you probably know that sound is a wave. You've probably heard people talking about like sound waves, okay? So just take your hands, stretch them out in front of you and clap. You are hearing a noise, right? So a sound wave is traveling to your ears, okay? Yeah. Obviously there's air in the room. We're going to do a whole lesson on sound later. There's air in the room and your clap is moving particles of air. So I just want you to think about what actually is a sound wave? Like, what does that mean? How is it? So I've got a question about that with another very creepy graphic. Sorry about this. A hand pats a table and moves an air particle. We'll simplify. We'll just say there's one air particle. Are you ready? This is awful. It's the best I could do. A douche. A hand pats a table. The air particle moves. The pat makes a sound which you hear. So where must the air particle have moved to? Has it gone A, towards the floor? Meow. B, away from you? C, upwards? D, to just outside your ear? E, to inside your ear? F is where it gets a bit confusing, D or E. F just means like somewhere near your ear, or G, it could have gone anywhere. You pat a table, so you disturb an air particle near the table, you hear the sound, where must that air particle have gone? You've got 5 seconds while I track down my coffee. Coffee, oh, there you are, coffee. What do you reckon? Okay, I'll tell you. The answer is G. It could have gone anywhere. It's a bit weird, right? But a sound wave only carries energy to your ear. It doesn't actually carry stuff. Come up here with me. Which kind of makes sense, right? Like when you hear a sound, because sometimes you hear a sound that's happened like a mile away maybe, and it gets to your ear pretty fast. It's not because a particle of air has whizzed through the air and got to your ear. It's more like dominoes, right? So you disturb some particles of air, they bump into other air particles, which bump into other air particles, which bump into other particles, which eventually make the air particles like right next to your eardrum move around, and they bump into your eardrum, and your brain turns that into noise that you understand because magic. So yeah, sound waves are a bit like dominoes. Because it's IGCSE, here's a diagram that I found on the internet. Here we go, this is a tuning fork, and this is a very common way of drawing a sound wave. So you've got areas of compression and areas of rarefaction. So compression is where the air is kind of squished together, right? And then rarefaction is where it's kind of spread out. You can model a sound wave incredibly well using a slinky. So if you've got a slinky with you, you might have. Stretch it out, maybe stick it under your feet or something. And if you give it a ping, then you see, what I love about these waves lessons is this is not just a model of a sound wave. This is an actual wave. It's not like electricity where we just had to keep drawing things that weren't real. No, this is a wave. So I'm pinging a coil on the slinky, and that's making the next coil vibrate, which is making the next coil vibrate. And you can kind of see, can't you? The energy is getting passed along, right? So that is the same kind of wave as a sound wave. Okay. More pictures. Look, a lovely physics teacher on the internet took a picture so that I didn't have to. So she's captured the moment here of compression in the slinky. So you can see these bits are stretched out, and this sort of area of compression is travelling along the wave. And Alice, in the Facebook lesson I did of this version, tells me that this is Japanese. Doesn't mind if you don't speak Japanese. They've used the international language of bashing something with a hammer. They've got a block of, so it looks like flesh. I'm sure it's not. But they've whacked it with a hammer, and you can see the dark area here is where those particles have been compressed and those vibrations have travelled through the block. So obviously the particles in the block are not moving from one end of the block to the other. But if you put your ear against this end of the block, flesh, whatever, you would be able to tell that energy had travelled through the block, because when the energy got to you, you'd probably get hurt, right? Okay, so that is a sound wave. The posh word for it is a longitudinal wave. So any wave that behaves like this, like sound, or what I just showed you with the slinky, is a longitudinal wave. And it means that the vibrations are travelling in the same direction as the way that energy is being transferred. Okay, so I pinged it like that, sort of to and fro, and the energy moved to and fro. Okay, so that's longitudinal. There is another kind of wave you can make with the slinky, which is the obvious one, I suppose. If I gave you a slinky and said, hey, can you make a wave with this slinky? You'd probably, try and get my hand in the shot, you'd probably do this, wouldn't you? Yeah, so that is a wave. This, you would call this a mechanical wave because it's been made with like a physical spring. We'll learn about like light being a wave later. Yeah, this is a mechanical wave. Can you see the difference? Bearing in mind we're talking about like vibrations and the direction that energy is being transferred. I could just do this all day. Yeah. That kind of wave, sorry Slinky, off you go, is called a transverse wave. So an ocean wave is a transverse wave, right? You can tell, it looks like one. And the difference is the vibrations move at right angles to the direction that the energy travels. Is that okay? So obviously when I wiggled my slinky, I was moving it, let's say, up and down, but the energy was still being transferred across, right? Like from left to right or whatever. So these are the two different types of wave. There's only two. You need to know the transverse wave, where the vibrations and the direction of energy transfer are at right angles, and the longitudinal wave, where they are parallel to each other, right, moving alongside each other. And all waves, this is the bit that is weird, I think. All waves carry energy, not matter. Look, it's even in your specification. You have to know that waves transfer energy without transferring matter. So, you know, matter's just like a posh word for stuff, right? So the longitudinal wave, the kind of dominoes particles booshing into each other, I instantly understand how that transfers energy, but the air particles aren't like moving. But with the transverse waves, it doesn't seem as intuitive. Like this picture of a ship, right? If you imagine it moving, which direction is this ship moving? So we've got a ship here on transverse waves, right? Like ocean waves that kind of go up and down. The ship isn't, if these waves are kind of bashing into it, it's not going to be flying off to the right, is it, at the speed that the waves are travelling? It's actually just going to be going up and down because the waves aren't carrying water particles and the ship along with them. The waves are just carrying energy. So like, because if you're on a beach and you see a wave lap onto the shore, you sort of imagine that like those water particles have travelled for thousands of miles, but that is not necessarily the case. Obviously water particles can and do move in the ocean because differences in temperature or whatever, but an ocean wave doesn't have to move water particles. It could just be water particles just doing that. And I don't want to spend any longer on this. Can you tell that it's just kind of blowing my mind a little bit and confusing me? But just to really hammer that home to you, if I do a transverse wave with a slinky again, keep your eye on one bit of slinky, right? On one coil. Obviously, when I make a transverse wave, like an ocean wave is with a slinky, the coils aren't moving, are they? So it does make sense, like if you imagine a boat here, bobbing up and down on this wave, there's no reason for it to move. Yeah, there you go. Anyway, right. So that's possibly a bombshell. Waves carry energy without transferring matter. All right, I think you're ready for this, you know. I think you're ready for my sheet. I've done a lot of talking. I've just got a very simple sheet for you here. If you go to my Facebook group, you will find that the worksheets are available to print off. But I always say, this is all available on BBC Bite Size, right? You don't need super neat versions of these notes, I don't think, unless it pleases you. So if you want to just think about the answers by looking at the screen or just put a few ticks on a piece of paper, feel free. We've got transverse waves and we've got longitudinal waves. And I just want you to tick what sentence relates to them, okay? So I've done one for you. Transverse waves transfer energy. Do longitudinal waves transfer energy? Do both kinds of waves transfer matter? Are the energy and vibrations at right angles to each other? Are the energy and vibrations parallel to each other? Can you write 2 examples of each? I regret that question. I wish I'd said 1 example of each, but it's too late now. Go on, have a go. I will never ask you anything that I haven't actually taught you, so you should be able to come up with 2 examples of each. And if you've done, are dominoes falling a wave? What do you think, based on what we've just discussed? Is a line of dominoes falling over a wave? For the dominoes question, it's not really the answer that I'm interested in. It's your thought process. How are you getting on? Have a think about the dominoes. I'll give you, 15 seconds. Okay, let's go through it. Do longitudinal waves transfer energy? Yes, they do. Yes, it's like the whole point. Do they transfer matter? No, waves do not transfer matter, no. Energy and vibrations are at right angles to each other. That's the transverse wave, yeah? The ocean wave. So you wiggle it in one direction, say up and down, but energy gets transferred side to side. So that is the transverse wave. And the longitudinal wave, what I call the kind of things booshing into each other wave, the energy and the vibrations are parallel to each other. One example of a transverse wave is an ocean wave, and another one is a slinky, and the longitudinal, I've said that one example is a sound wave, and I've also written slinky. What have I done wrong here? Why am I deeply regretting those answers? Say that was like a 4-mark IGCSE question. It's a 4-mark IGCSE question, 2 examples of transverse waves and 2 examples of longitudinal waves, and I've written ocean wave, slinky, sound wave, slinky. What have I done wrong? And what can I... It's not that the answers are wrong, it's... Well, go on, 10 seconds. How do I improve those answers to get 4 marks? I clearly know what I'm talking about, but I haven't written the right thing to get the marks. So I think... Come here. I think you probably would get a mark for slinky because it is a wave. It's not just a model of a wave, it is actually a mechanical wave. But the problem is, if you write that slinky is a transverse wave, you're not telling the examiner that you know what you're talking about, are you? Because you could be saying, oh, you ping a wave and you get a transverse wave. So I really would have had to have said a transverse wave would be a slinky where the slinky was vibrated at right angles to the direction of energy transfer, which is why you should just write ocean wave. By the time we get to the end of the module, you'll know loads of transverse waves, like microwaves and light and stuff like that. Okay, are falling dominoes a wave? Well, I have some dominoes here. Let's watch them and think about it. You ready? Oh, so pleasing. Is that a wave? I'm saying yes, it is. I'm saying yes it is because I looked it up on the internet and most scientists seem to be agreeing that it was. But also because energy is being transferred, but matter is not being carried along, right? Moved. So the domino at the front doesn't move along to the end of the wave. So matter isn't being moved, but obviously energy is being transferred because the last one falls over. So if you said yes for that reason, well done. If you said no, because you've picked up on the fact that waves seem to involve vibrations and that dominoes aren't like technically vibrating, are they? This is one falls over and then that's it. So if you said, well, there's nothing vibrating, so no, it's not a wave, well done. I don't think that's probably right. I think it probably is, but I'm very pleased with your thought process, which is the most important thing. Okay, if you look up wave, kids, activity, science on the internet, it will tell you to get a bottle, fill it with blue liquid, maybe stuff it with some plastic sea creatures, because irony, and then move the bottle from side to side. And lo, you have made a wave in a bottle. Please, if you have brought a bottle of something to do this, just keep the lid on and don't hold it over your computer. Do you think that that is a wave? Just have a look at it. We're not going to bother to colour it in and add the plastic, but do you think that that's a wave? So at the moment I'm tipping the bottle up and then I'm tipping it down and I'm tipping it up and I'm tipping it down. Is that a wave? And why? Why not? So I was saying definitely not, because I'm just sloshing matter, like particles, from one side of a thing to another side of a thing. I've put a leaf in there because I wanted to see if it was actually moving matter. So I was saying no, because it's just moving matter. But actually a lot of people on Facebook were saying yes, and I think I kind of agree with them now. You can definitely move it so that a wave does appear, don't you? So that you get this kind of hump, so it would be a transverse wave. So yeah, maybe I was a bit mean to the science fun kids activity. Last question, is a wave a wave? Have I ever said a weirder sentence in my life? Is a wave a wave? Go on, have a go. Think about it. Why? Tell me why. Give explanations for your reasons, answers, words. Come on. What do you think? Why or why not? Oh, it's nice. Like 5 new people just arrived to watch live as I was waving. Maybe YouTube can detect waves and it attracts people. I should try that more often. We are discussing whether a wave is a scientific wave. It's not, is it? It's definitely not. Why not? Well, it's transferring energy. Waves do transfer energy, and if you put your face in the way of your hand, you can feel that energy is definitely being transferred to your face. But it's moving matter, isn't it, as well? It's not, matter is definitely being transferred. It's just moving a thing. It's not a wave. But you may have noticed, and well done if you did, if you attach something like a piece of string or a slinky to a wave, like a hand wave, then that does make a wave. Yes, absolutely. So your hand is, well, in posh IGCSE language, which we'll learn later, you would say that your hand is oscillating, like it's moving from side to side. It's kind of vibrating. And that does create a wave, but a wave in itself is not a wave. Have I said wave enough? No, I haven't. Last thing, please get a mug of water, or like a plastic cup of water. Can you make a longitudinal wave and a transverse wave using your cup of water? Keep the water in the cup, and it doesn't have to be both waves at the same time. 10 seconds, get a cup of water. Can you make a longitudinal wave and a transverse wave with your cup of water? Go. 1. Helps if you've seen Jurassic Park. So, yeah, that's a good one. So, I think if you wiggle it, you get a transverse wave. Did you do that? This might be a little bit just believe what I say and not what I show you, but if I wiggle this cup really fast, I can just about get 2 peaks to appear on the surface of the water, which is a transverse wave, right? The 2 peaks of the transverse wave. Just about. I think you can get a longitudinal wave by just tapping the cup. You must be able to, right? Because you can clearly see that the surface of the water has been disturbed. And that must be because energy is being transferred from the bottom of the cup all the way through. So the water particles like booshing into each other and getting to the top, right? Must be. So that must be a longitudinal wave. Like one of the greatest moments in the greatest film ever made, you know, where the T-Rex arrives. Oh, someone pointed out on Facebook yesterday, it's genius, that if you blow on the top as well, did you do that? Then you get ripples. That's definitely a transverse wave, isn't it? On the surface of the water. So, are ripples waves? Yeah, definitely. Of course they are, aren't they? It's still energy being transferred, not matter. Right. So, I just need to introduce a new word. I'm not going to use it too much today, but I will later. At GCSE level, instead of saying the direction that the wave is travelling in, we tend to say the direction that the wave is propagating. Ooh, brilliant word, propagation. I'll tell you why. Direction of propagation basically just means spreading out. Is this a little bit more accurate? Because if you imagine you make a sound, if you imagine what the air particles do, it's sort of more like they spread out in all directions, yeah? And it seems obvious, but when we're drawing waves later on, we obviously, for simplicity, you end up just drawing like a straight line from the clap to the ear, and you can kind of get the impression that sound waves are just like neat little rows of dominoes. But obviously, if you make a clap, the air particles are like vibrating out in all different directions at the same time. So rather than saying like the direction the wave is travelling in, it's the sort of thing, you know, you say at Key Stage 3 because it's simpler, but at IGCSE it just helps us to remember that it's propagating, right? It's spreading. It's a good word. Okay, very quickly, just so I can say we've used the word propagation. Can you complete this sentence for me? Know that for a transverse wave, the direction of vibration is at something to the direction of propagation. What a sentence. Know that for a transverse wave, so like an ocean wave, the direction of vibration is at something to the direction of propagation. Here's a diagram to help that make sense. Vibrations, up and down, propagation, side to side. So it's at right angles, right? Transverse wave, the vibrations and the way it spreads out are at right angles to each other. Whereas for a longitudinal wave, the direction of vibration is something to the direction of propagation. Longitudinal wave, particles booshing into each other, and the wave spreads out in the same direction. So you would say that they are parallel. Yes? Good. All right, we're nearly there. We just need to talk about bits of waves, like how you describe waves, because that'll be useful for the next 11 lessons on waves. First one, this is the wavelength. A wavelength is just how long a wave is, right? It's the complete wave, like the length of one complete wave cycle. So here we've gone from peak to peak, all right? The wave is at its peak. It goes all the way down, it passes the midpoint, it goes right down to the bottom, comes up again, it passes the midpoint again, it gets right to the top. And can you see that then we start repeating? Like we've already measured a bit of wave that's at the top and going down. So that's one wavelength. But there's loads of different ways you can measure it. So if we start from the midpoint, the wave goes all the way up, comes all the way down again, gets all the way up, and then it starts repeating again, right? So that would be a wavelength as well. Or if you wanted to, it'd be a bit weird, but you could do it, say, from the middle, start from the middle, goes up, goes all the way down, starts to go up again, and then it starts to repeat. So that would be one wavelength. Is that a wavelength there? It's number 3. So we're measuring from the midpoint, the wave goes all the way up, comes all the way down. Is that a wavelength? No, it is not. Well done if you said that. It is half a wavelength, isn't it? Because we haven't started repeating it. You've also got to measure as the wave goes all the way down and up again. It seems obvious. I got this catastrophically wrong in the first lesson I did and had to improve it. So it's very easy to, if you're not thinking carefully enough. And the second one we're going to teach you at the moment is amplitude. Amplitude is the maximum vibration. It's like as far away as the wave gets from this, what we'll call like the equilibrium or the midline here. It's very often tested because a lot of people think that it's the length from the top of the wave to the very bottom of the wave. It is not. That is not amplitude. This is amplitude, say, from the equilibrium to the very bottom. It's just the maximum vibration from the midpoint. Okay, are you ready? Have you got it? Let's see. Number 1, is this amplitude? You've got an arrow going from the midpoint to the top of a wave. Is it amplitude? 3, 2, 1. Yes, it is. Well done. Is this amplitude? You've got a line going from the midpoint all the way to the very bottom of a wave. Is it amplitude? 3, 2, 1. Yes, it is. Yes. Is this wavelength? You've got a line which is measuring from the top of one wave to the top of the next wave. Is that wavelength? 3, coffee, 1. Yes, it is. Yes. Next one. Is this wavelength? We're now measuring from the midpoint. The wave goes all the way up, comes all the way down, all the way back to the midpoint. Is that wavelength? Is it? Yes, it is. Yep. Because you can see, right, it doesn't repeat throughout that whole area of measurement there. And then it does start to repeat. It starts to go up again. So that's right. Is this amplitude? An arrow stretching all the way from the top, all the way down to the bottom. Is it amplitude? 5, 4, 3, 2. No, it's not, is it? No, that's like 2 amplitudes. Is this amplitude? Tiny little arrow going from the midpoint down to the bottom of the wave. Is that amplitude? 3, 2, 1. Yes, it is. And is this wavelength? Is that wavelength? Going from the middle, and then it goes down and up and then down again. Yes, that is wavelength. Is this wavelength? The wave goes from the middle, all the way down, all the way back up. Is that wavelength? 3, 2, 1. No, it's not. No, because it hasn't started repeating. We've got all this top bit of wave to measure as well. Okay, let's throw a few more in then, since we're all enjoying this so much. The crest or the peak is the top of the wave. That's nice and easy, isn't it? It's super easy. If you've been surfing, then you might have surfed the crest of the wave. And if you like hiking, you have climbed up to the peak. So both those words mean the same thing. And the trough is just the very lowest bit of the wave. Okay. Frequency, and we will talk, I kind of wish I hadn't added this to the end of this lesson now, but it's too late because I've already taught the Facebookers it and we all have to be in the same place. So sorry, there's 2 more bits of information. But don't worry, because we will be covering it again if your brain is a little melted. Frequency is how many waves per second, right? So here we've got on the x-axis time in seconds, and let's see, we've got a full wavelength going up and then down and then up again. We've got another full wavelength up and then down and then up again, and at that point 1 second has gone by. So if frequency means how many waves per second, what is the frequency of this wave? Frequency is measured in hertz, by the way. We sort of touched on that when we did electricity, didn't we? Hertz just means per second. It's big H and a little Z. Hertz means per second. What's the frequency of this wave? It is 2 hertz because there's 2 waves happening in 1 second, right? One wave, another wave. So that's your frequency. Whew. Got it? Let's see. And if you haven't, it really doesn't matter. Is the frequency of this wave 1 wave per second? Is the frequency of this wave here 1 wave per second? So the wave starts at the midpoint, it goes up, it goes all the way down, it comes back up again, and in that time, well, and as that happens, 1 second has gone by. The answer is yes, the frequency of this wave is one wave. There's one wave happening in 1 second. So yeah, that's 1 wave per second. Is the frequency of this wave 2 waves per second? What do you think? Is the frequency of this 2 waves per second? 3, 2, 1. Yeah, it is, isn't it? 1 wave, 2 waves in 1 second. Is the frequency of this wave 2 meters? Is the frequency of this wave 2 meters? 5, 4, 3, 2, 1. No, it's not. It is 2. Well done, if you saw that. But yeah, no, frequency isn't measured in meters. Frequency is how many waves per second, so it's got to be hertz. Is the frequency of this wave 2 hertz? 5, 4. Just shout yes or no into the ether. 3, 2, 1. Yeah, it is. Because there's 2 waves happening in 1 second, and hertz means per second. Splendid. Is this the crest of a wave? You've got a star on the top of a wave. Is that the crest? 3, 2. Shout at me, shout. Yes, it is. Is this the peak of a wave? You've got a star right at the bottom of the wave. Is that the peak? 3, 2, 1. No, it's not. Is this a trough? A star right on the bottom of the wave. 5, 4, 3, 2. Yes, it is. Yes. Is this half a wavelength? Is it? Is it half a wavelength? Starting at the midpoint, equilibrium, then going all the way up and then coming down. Is that half a wavelength? 3, 2, 1. Yes, it is. Yes. Whew. Is this the peak? A star at the top of a wave. 3, 2, 1. Yes. Is the frequency of this wave half a hertz? Is the frequency of this wave 0.5 hertz? You start at the midpoint, it goes all the way up, and then it comes back to the equilibrium in 1 second, and then it goes all the way down and comes back to the equilibrium in 2 seconds. So is the frequency of that wave half a hertz? Yeah, it is, because frequency is how many waves per second, and in 1 second, half a wave has gone by, right? You need, in 2 seconds, you've got 1 wave. 1 whole wave. So in 1 second, you've got half a wave. So that is right. Okay, last thing. Right, I'm just going to show you my face. Show you my embarrassed face, right? Teachers in classrooms, like when I was a teacher in a classroom, right, you could teach a lesson and it could go really badly. And then you could be like, oh, well, I'll change it for next time and no one will ever know. I can't really do that because anything I've taught in the Facebook lessons, I have to teach you in this lesson because otherwise we'll all be out of sync. So just my confession that this last thing would definitely be cut out if I was a classroom teacher, but now I have to tell you it. But don't worry if you're just like, I cannot take any more from you, Lara. That's fine. We will do a whole other lesson on this. I just wanted to introduce all the kind of key points, all the key words. But yeah, drink some of your water from your plastic mug. Stay hydrated and relax if you've had too much. Period means how long it takes a wave to complete a full cycle. So frequency is how many waves per second. Period is how long it takes for a complete wave to happen. I think it's kind of easier than frequency. So here we've got 1 wave happening after 2 seconds. So the period of this wave is 2 seconds. It takes 2 seconds for 1 whole wave to pass by. So the period of the wave is 2 seconds. All right. Here's the sheet that I regret. I've done 2 waves here. Can you tell me the frequency of each wave and the period of each wave? And I've done a reminder. Frequency means the amount of waves per second, and period means how long a full wave takes. So the first wave, you've got, it goes up and then all the way down and back to the middle again in 1 second. So what's its frequency and what's its period? And the second wave, it goes all the way up, comes all the way down, goes all the way up, goes all the way up, comes all the way down, comes up again, and that happens in 1 second. What's the frequency and the period of those waves? Check the time. It's actually not that, it's not that late, is it? I've absolutely rattled through it. You ready? I'll go through the answer because you've either got it or you're not understanding, at which point this will be a bit painful for you. The frequency of this wave, how many waves per second? Well, it's 1 wave in 1 second. So it's 1 wave per second, right? In 2 seconds, you've got 2 waves. If we extended this graph in 4 seconds, you would see 4 waves. So it's 1 wave per second. And the period, how long a full wave takes, is also 1 second. The second one, what's the frequency of this wave? Right, how many waves per second? 1, 2. 2 waves happen in 1 second, so the frequency is 2 hertz. And the period, how long it takes for a full wave to happen, is, well, you get 2 waves in 1 second, so 1 full wave happens in half a second. So that's the period, 0.5 seconds for you. Okay, that, folks, is the end of the lesson, except I also actually have some past paper questions that I made up to put on the screen. So I will show you those, and then we'll quite quickly go through the answers to those. If you fancy testing what you've learned, I better do my little ad, just in case some of you are new and don't know how this is my job. This is my job. If you've seen my ad and you're supporting me already, don't forget, on my Facebook page right now is a post that says, hey, if you're watching on YouTube Live, you can comment here and I'll say hello. So if you go over to my Facebook page now, like open a new tab, you'll be able to find that post, and you can hammer whatever you like, you know, just, you could be mean, you can be friendly, it all helps the algorithm, don't worry about it. If you would like to support me, then you can. If you're enjoying these lessons, then you can, in my About section on YouTube, there's a link to this website called Coffee. So enough people are going to my Coffee website and supporting me with £5 a month, that this is literally my job. It's amazing. So everything is free. Oh, in fact, yeah, I haven't said this to the IGCSEs for a while. All the printouts are in my Facebook group, and those are free. All the lessons are streamed for free, like this. They're all saved on YouTube for free. There is no paywall. I couldn't deal with the admin of that. And I also, in my Facebook group, have a PDF of where I put like homeworks and useful links to like maybe past paper questions that I think you should be able to do after this lesson. So I'm going to put that up today. So if you want more past paper questions, you can go there. And yeah, enough people are supporting me on Coffee that it's a job. It's amazing. So if you go to Coffee, or just type Coffee Theatre of Science into the internet, I will send you Theatre of Science magazine. It comes out about 5 times a year on average. It's just, you get it whenever I've written it. But this one's on mould. This is the one you'll get if you sign up now. It's got a beautiful comic about mould. It's got a free biodegradable plastic bag with it, so that you can grow your own mould and use the mould spotting guides to identify it. It's a different subject every time. I'll send you some rainbow glasses, which will actually be incredibly useful when we talk about waves. I'll send you a sticker if you're into that kind of thing. Right. Let's do some GCSE questions, and then I'll go to my Facebook page and see who's saying hello. Here we go. Right, GCSE questions. A and B are illustrations which have been drawn of sound waves for a children's book. Can you explain which diagram is more scientifically accurate and why? Right, so diagram A has got someone playing a trumpet and a wave coming out, which sort of looks like an ocean wave, right? It's like a wiggly worm travelling from the trumpet into a person's ear. And diagram B is a stereo with kind of lots of separate waves all sort of pushing into each other towards the person's ear. Which one of those is more scientifically accurate? Which one's a better drawing of a sound wave, and why? Question 2, can you give an example of a transverse wave? Question 3, what is the frequency and period of this wave? So you've got a wave which goes up and then all the way down again and comes back up again, and that takes 2 seconds. Basically, it takes 2 seconds for one whole wave to travel. What is the frequency and the period of that wave? And question 4, I might have got a little bit carried away with the letters here. You've got a diagram with all kinds of different things labelled on it with letters. And can you tell me which letters, it could be more than one actually, represent amplitude, wavelength, crest, and peak? So A is measuring from the very top of a wave down to the very bottom of the wave. C is measuring from the equilibrium to the bottom of the wave. H is from the top to the midpoint, but it's kind of on a diagonal. B is stretching all the way from the start of the graph where the waves are at equilibrium to 2 peaks away. F is going from peak to peak, and E is going from trough to trough. G is at the very bottom of the wave, and D is at the very top of the wave. Which one of those are amplitude, wavelength, crest, and peak? I'll give you another 15 seconds. Question 1, I should say, by the way, has 3 marks available. 3 marks available for question 1. All right, here we go. Question 1. You don't usually get a mark at IGCSE for just saying the right answer. You usually have to explain it. I mean, I have made this up, actually, I must admit. You get 1 mark if you've said that sound waves are longitudinal. Give yourself another mark if you've pointed out that B is a sort of diagram of a longitudinal wave. And if you've explained why that is, it's because the vibrations are in the same direction as energy transfer, give yourself another mark. You could have said the complete opposite and got marks as well. So you could have said A is a transverse wave because the vibrations are at right angles to the direction of energy transfer, and sound waves are not transverse waves. So that would have been fine as well. I'll put that answer up small in the corner in case you want to write that down. An example of a transverse wave, from this lesson, you should have written ocean wave, really, unless you were brave and wrote, a slinky vibrated at right angles to the direction of energy, just write ocean wave, yeah. The frequency of this wave, how many waves per second? How many waves per second? It's actually half, isn't it? Half a wave has managed to travel in 1 second there, so it's 0.5 hertz. If you remember that the unit is hertz, very well done. Give yourself a mark for 0.5 and a mark for hertz. The period of this wave, what's that? How long it takes a wave to travel. How long it takes 1 complete wave to travel. So that would be 2. We will do loads more on that later, don't worry about that. And this letter 1, the amplitude could only be C, but the wavelength actually could be F or E. It couldn't be B because B is too long. And the crest and the peak are both the same. They're both D. So sorry, that was possibly a little bit mean there. And that's the end. Phew. That felt like a very dense lesson. I mean, they quite often are actually, aren't they? Okay, I'll flip you back up again, just to say cheerio, and have a look on my Facebook page. Hello. Yes, because there's no comments on YouTube, which a lot of people prefer actually. Some people find comments quite distracting. I do put up a post on my Facebook page saying, if you want to say hello, then please do. I must say, YouTube's really useful because it lets me store them, which means that people can watch on catch-up, which is obviously very useful. But I do really, really appreciate people coming live because it makes such a difference. If I logged on and there was no one here, I'd be like, oh, cool, I'll just do it later. And then I would never do it. And then literally my business would crumble. I am not exaggerating. I have to have, as long as there's one person watching, I'm like, oh, it's okay. I have to do it. And then it gets done. So thank you very much. Oh, look, comments. Oh, no. Oh, wait. Let's just click refresh just in case. Otherwise, it's Heidi, who is maybe watching right now. Hello. Oh, you watched live today. Oh, brilliant. Hello. Hello, Caroline. Good to see you. All right, you lot. Well, if that's it, I'm going to rush over to my Facebook page where I'm teaching this lesson again in 15 minutes. And if you are watching this and you like YouTube lessons, then tomorrow at 2 o'clock, I'm doing my Lego story time and we're doing a dandelion dissection tomorrow. That's Thursday, tomorrow, on YouTube. Or it's also on Facebook at various times. Right. Oh, is that Betty as well? Hello, hello. I'll see you soon, you lot. Bye.